So I was talking about about uh, how to switch between the controllers in the general case when the state space representation of the controller is given like this. And I also showed you that it is very realistic that the controller can be represented in this form. Sorry, in this form. Okay. Now, what is the goal? The goal is when we switch between the controllers. When we switch between the controllers, we want to avoid the transient response. We want to eliminate the transient. So how we can do that? As it is shown here, it's actually similar to what I said, but it's at least in terms of getting feedback from the output which is selected. So basically what you do, you calculate U minus UI for each controller, and then you feed that back to the controller, and you will take it into account in the dynamics of the controller. So if I go to the next slide, the controller used to be only this part. We have added this term to the controller. Okay, so for each controller, we have added one extra term, and this extra term is Li multiplied by U minus Ui. Back to the previous slide. If the first controller is selected, which means that the first controller is active. If controller number one is active, it means that U is equal to U1. Therefore, U minus U1 is 0. Therefore, this term is being added. It doesn't change anything for the active controller because it is simply 0. So this term is being added for the one which is not in the loop. Okay, so this is active, this is not active. So for this controller, you always take into account what is the output of the controller being applied to the system, and then you subtract the output of this, the ICE controller, from the selected output, and then you feed that back. So now if you look at this dynamic, as I mentioned, for the active controller, this one doesn't do anything. For the inactive controller, what happens is that, okay, this one is being affected, the dynamics is affected, it affects the dynamics. So what happens, basically what you can do, because you have Li, Ui, and Ui is the output of controller. So basically what you should do, you should substitute Ui from the second equation. You should, because you have Ui here, you have added this term to the first equation, and Ui is being given here. So you substitute Ui from this equation, you bring it up. For example, the first term is C multiply X. So then you have Li minus multiply minus C multiply X, and you have another X here. Therefore, if you factor from X, it would be AC minus, the phrase you have here. It would be AC minus Li C sub Ci multiply X Ci. Okay, so it will actually change all terms in the first equation, but the most important term is actually the one that you have here. Why the first one is most important one? Because in the left side you have X dot of Ci. If you remember from COS, when you have X dot Ci in the left side and in the right side you have this phrase multiply X Ci, the stability of the whole controller. So the stability of the controller depends on the eigenvalues of this matrix A minus LCI. Okay, therefore we should select Li such that the eigenvalues of this matrix are in the left side. Why we need to do that? Because we want to have the not active or non-active controller to be stable. We want to avoid the states of the non-active controller to diverge, Because if we make sure the controller, the non-active controller, is stable, then therefore we can say that the states are limited. They don't diverge. They don't explode. Because in principle, they can diverge. And always remember that this extra term we have added to the first equation, it doesn't affect the active controller. It doesn't do anything in the active controller because U is equal to UI for the active controller. Okay, which means that you are not actually changing the performance of the controller at all because the active controller is doing the same. But when the active controller is connected to the system, you are taking care of the other controllers not to explode. Okay, so also it can be shown that actually they can follow U to some extent, and okay, that's the story. Okay, it's a bit crowded, but I have shown you only two controllers here. So you see that actually, this is actually, for example, XC1 dot, which is the input of this integrator, is AC1 multiply XC1 and then BC1 multiply YRF. So it's exactly what you had in the equation, but you have this extra term here, L1 multiply U minus U1, and U is here. So you have a feedback here, and also you have a feedback here for the second one. As I said, if this figure shows that the first controller is active, therefore this term, because U is equal to U1, so it doesn't do anything, and so on. So when I said, as I said, if you, for the non-active controller, if you substitute UI from the second equation to the first equation, you will get something like that. I just explained the first term, but also it will affect the other terms as well, because UI has something from YREF and also has something from Y. So if you multiply Li by UI and then subtract it from the first equation, it means that actually it will change all these matrices. And also it is recommended, if possible, try to select Li from this equation, because if you select Li, it is not necessary, first of all, because as we said, Li should be selected such that the eigenvalues of this matrix, LAC minus LICI or CCI, the eigenvalues are in the left side, in the left half plane. Doing this, as I mentioned, it guarantees that the non-active controller doesn't explode. The states of the non-active controller will remain limited. But you know that A minus LICI, if you want to select the eigenvalues in the left side, there is not a unique solution for Li. Infinite solution you can find, because it depends where you want to place the eigenvalues. So, but because first of all, because you want to stabilize that, then the pair A and C, they should be detectable. Sorry, they should be detectable. Because if A and C are not detectable, I think I talked about detectability a couple of weeks ago. I said that we have observability and also we have detectability. Observability means that eigenvalues can be selected wherever you want. Detectability means that those eigenvalues which are in the right side, which are unstable, you can place them wherever you want. But some of the eigenvalues can be non-observable, but they should be already stable. So anyway, that's something from before. So you know that ACI and CCI should be detectable in order to have this condition fulfilled, which means that the eigenvalues can be selected in the left side. But this Li, if you can select Li like that, and it also fulfills that condition for the eigenvalues, then it also helps because it if you select this one Li from this equation, it will actually make the coefficient of yref to be 0. It means that actually the states of the output of the non-active controller will actually remain closer to the output selected. Because what we want to do, let me go back to the slide that we had this. Okay, we have these controllers. As I said, when you switch between the controllers, you might get this transient response. But the transient, what is the source of that? The source of that could be the states of the non-active controllers are being diverged. So they have gone their own way. So they don't pay attention to what is being selected. They are working for themselves and they have exploded. And when you switch to that controller, it takes time to bring them back, to recover from that state. So what we do, we make sure that it is stable, first of all. So we don't let them to explode. And also, if we can take care of the output of the controller to be, of the non-active controller, to be as close as possible, as closest as possible to the one selected, it would be better. So those extra efforts we are doing, for example, this equation, it helps to have a better response. Any question? This is basically the end of the last slide for this transient elimination. So I just explained. Yeah, go on.
Sorry, I have a question about the first method that you said. That you said that's the simplest method that we can use.
Yeah.
In the step when we were in the nth step and we wanted to calculate u of u at n, then we said that we should use the history of the first input u1, and in the next step, if we are going to calculate un plus 1, then we should use, for example, because we need n minus 1 and n minus 2, so we need to use, one of them should be from u1 and the other one should be from u2.
Yes, and that's actually the last step, because from the next step, then you can only switch on this u2. So the transient, it takes only 2 sample time. If you take care of that, then you have controlled that, then you're fine. Is that clear? Okay. But as I said, the key point is actually to implement it like this. So basically, because any discrete controller can be implemented using these Z inverse blocks, but the point is, instead of getting feedback from the output of the controller itself, just get feedback from the one is being selected. So this is the first order, but if it is a second order, then you need 2 of these Z inverse blocks. Do I need to also show you how to implement this one, or it was clear? I think it was clear. You just need to have 2 of these Z inverses. Okay, let me continue the lecture and talk about the other methods we have, and hopefully we have some time at the end to simulate at least. I have also some examples, but I believe if we can simulate, it would be better. Okay, am I recording, by the way? Yes. Okay, the next method for controller reconfiguration. It's called model matching. What does that model matching mean? Imagine that you have actually designed, because when you design a controller for a system, let's say for a fault-free system, for the system that doesn't have fault. Imagine that you design a state feedback controller. And the state feedback controller, the way you find the feedback is K. If U is equal to K multiply X, or U is equal to K multiply Y. So I will tell you actually the difference later. But however you design the controller, basically you have spent too much time, and in many cases the controller, designing a controller is not just one step. You design a controller, you apply it to the system, you observe the results, you refine the parameters, you fine-tune the parameters, and then during actually a process, you will find the best values for the parameters. So it's not like that you, for example, you design an LQR controller, because LQR, the result of LQR problem is a state feedback controller. So how to find the state feedback? You could define a cost function and then try to minimize that, and the result would be a state feedback. But that cost function, you have some weights, and you play with the weights. For example, you increase the weight of the state or the weight of input in order to get the best result you can get. So the controller design is an iterative process. That's what I want to say. And you do that, and then later you see that, okay, you need to take care of a fault as well. So you have spent enough time for the fault-free case, and now you need to think about the faulty case. And you say that, okay, already you have spent enough time to find, and when we say, okay, to design a state feedback, it means that already you have spent enough time to find the K matrix, because U is equal to K multiply X. Okay. So, and you say that, okay, the eigenvalues of A minus BK are at the right place and at the best place that you could have, because you have spent enough time this back and forth to fine tune them. Now you say that, okay, when you want to design a controller for the faulty case, okay, when you want to design a controller, is it possible to make it work the same as the fault-free case? What does it mean? It means that for the faulty case, can we have a controller such that the A minus BK in the faulty case is actually the same as A minus BK in the no fault case? So this is actually what we are going to do here. In the model matching, and the idea is that we have spent enough time to design the original controller, or we can call it nominal controller. I think this term, I like this phrase, this nominal. Nominal controller means that a controller that has been designed for the fault-free case. So we have spent enough time, and when we want to design a controller for faulty case, we don't want to again spend time and then go to this back and forth situation. That's one thing. And the second thing is that in some cases actually it's not because a fault should happen, and maybe, okay, if it is a fault in the sensor actuator, that's not difficult, you can do that. But if it is a fault in the system, maybe you cannot actually make it happen easily. So you know what happens in the model, but it's not easy to go through that iterative process and see what happens in the real system and fine tune the parameters. So the idea is to use the nominal controller to tune the parameters of the other controllers. Okay, so that's the idea. In general, the system could be a nonlinear system, but what we are considering in this course is a linear system. So it was actually better if I had written the linear equations. And you remember, I don't know if you have had this case, or if you remember, in general, we could have a state feedback or we could have a state output. State feedback means that u is equal to minus ky. Let me go to the next slide because at least we have some of them. This is state output. We say that for a system like this, x dot is equal ax plus bu and y is cx. One type of controller is just write u is equal to minus ky. It is not that common. It is not that common, but in some cases actually, because we are measuring most of the states, or even we have a system in the lab, the coupled tank system, the multi-tank system in the cyber physical lab, because we have sensor for each tank. And basically we can say that, okay, what if we define output to be the level of all tanks? So in that case, y is equal to cx, and c is the identity matrix, which means that actually because we are measuring all the states, so let's define y to be exactly I identity matrix multiply x. And in that case, when we say state feedback is the same as the state output. Sorry, output feedback. State feedback is the same as output feedback, because instead of writing u equal minus kx, we can write u equal minus ky. Okay, so in the rest of these presentation, we actually switch between the state feedback and the state output, because some of the methods are applicable for the case that you have a state feedback. Some others are applicable for the case you have a state output. Okay, so I will try actually to emphasize when we come to each algorithm. I try to emphasize it is applicable to what format. So this is the nominal system we have. This is the controller. For now, we assume that the controller is a state is output feedback, because we are feeding back only the output. And the faulty system is like that. So what is how we can show the faulty system? So because we have A, B, C matrices, so the fault, when the fault happens, it changes one of these matrices, or it could change, I mean, all of them. Can you guess if one of the actuators is not working, how we can show that? Let's say we have A, B, C matrices. One of the actuators is not working. Let's say we have two actuators. One of them is not working. Can you explain, or can you guess how we can show that fault?
One row split equals 0.
Exactly. One of the columns of B is 0. The one that actually is corresponding to the faulty actuator. And if one of the sensors is not working, the corresponding row of C is 0. Okay. So, and if something in the plan changes, then A will change. So basically, it's a general case that you can show all faults. And as I said, imagine that the controller, the output feedback controller design is minus ky. Now the question is, we want to design a controller, again, output feedback controller in the faulty case, such that, no, this is actually the question. Can we design a controller in this format, u is equal to minus kf multiplied y, such that a minus bkc is equal to af minus bf kf cf? First of all, why do we have a minus bkc? Do you know? Do you know where does it come from? A minus bkc.
I believe that's the first function of the solar system.
But did you say transfer function?
If you substitute u with minus ky.
Exactly. If you substitute u with minus ky and y is equal to cx, what you get is that x dot is equal to a minus bkc multiply x. If it is state feedback, then x dot would be a minus bk multiplied by x. If it is output feedback, then you have bkc. Okay, so this equation actually shows whether we have a state feedback or output feedback. And the reason is that some of these algorithms, as I said, they're only applicable for output feedback. So we need actually to pay attention which one is applicable. So the point is, as I said, we have designed a controller for the nominal system, and the controller is in this form. It is such that the eigenvalues of a minus bkc are at the right place. Now a fault has happened, or we are predicting if a fault has if a fault happens, how to design KF. Okay, so we still want to have the output feedback controller, but it should be a new controller because you need to change K, because K was designed for the case that we had A, B, C, but when we have AF, BF, CF, we need to design another K, and we call that K to be KF. The question is, can we achieve the same because in the left side we have one matrix, A minus BKC is also it's still a matrix. Can we get the same matrix here? So this is called model matching. But we will see actually. So for model matching, we have basically two different cases. So one, or yeah, I shouldn't call it cases, but we can either achieve exact model matching. Exact model matching means that, okay, we are able to find KF such that A minus BKC is exactly equal to AF minus BF KFCF. If it happens, we say that, okay, it is exact model matching. If it doesn't happen, but we can find KF such that the error between this matrix and the other matrix is small, then we say that, okay, we have model matching to a good extent. It is not a perfect, or it's not an exact model matching, but it is good enough. Okay, therefore we try to minimize A minus BKC minus AF minus BF KFCF. And this minimization, of course, because it's a matrix, it should be the norm of matrix that is being minimized. So we change KF such that this norm is minimal. So we will actually investigate three different cases. One of them is the sensor fault, the other one is the actuator fault, and the other one is when we have a fault in the plant. If it is the fault in the plant, there is a difference between this first case and the other case. And the difference is that if the fault is in the plant, then we should have a state feedback, not output feedback. You should have state feedback. But the other two cases are output feedback. We will see that actually when we get to that page. So this is the first case when we have this state feedback and a fault in the plant, and the fault could be in the plant and the actuator both at the same time. So if it is the case, what should we do, or what can we do? As I said, in the first case, we have a state feedback. Therefore, instead of A minus BKC, we have only A minus BK. So we are trying to minimize the norm of A minus BK minus AF minus BFKF. So we are trying to minimize this. Let me remind you of, we had a similar case in SSP, but let me remind you how we can solve such a problem. So I will switch to the other camera. Okay, we are trying to minimize the norm of A minus BK minus AF minus BF KF. Okay, what is the unknown here? The unknown is KF. Everything else is known. A, B, K, AF, and BF, they are all given. Okay. So if you remember from least square problem, the ideal case is that A minus BK is equal to AF minus BFKF. Let's write it equal, because that's what we are looking for. The ideal case is, as I said, is to achieve zero error. If I write A minus BK is equal to AF minus BF KF. Okay, so I will bring this term with KF to the left side, and I will bring the rest to the right side. Therefore, in the left side we have BF KF. In the right side we will have AF. So A has come to the right. It would be minus A plus BK. So this is known. This is also known. KF is unknown. Do you know what is KF from least square? Any idea? In least square, we said that if we have A multiply X is equal to Y, A and Y are known, X is unknown. Do you remember what was X? Least square. Okay, I was expecting actually that you remember, because it's if you want to memorize only one equation from SSP, it should be this equation, because it's very, very useful, very practical. So X is A transpose A inverse A transpose Y. Okay, and we call this one as the pseudo inverse of A. So also notation wise, we can write A plus Y. The ideal case was that if A is invertible, then we multiply A inverse from left, then X would be, so the ideal case is that X is equal to A inverse Y. But in many cases, A is not invertible because A is not even a square matrix. If it is the case, you calculate the pseudo inverse. So this is what we call pseudo inverse, and this is actually how you can show that in mathematics. A plus means the pseudo inverse of A, which is A transpose A inverse A transpose. In MATLAB, I think we have tried that. In MATLAB, if you type P-inv, and P stands for pseudo, P-inv of A, it will give you this A plus. Okay. Or if you write A backslash B, A backslash Y, it will give you the pseudo inverse of A multiplied Y. Okay, back to this problem. What is KF? And when I say what is KF, if you minimize these, because it was the same here, AX equal to Y, it doesn't have any solution. So what we do, we try to minimize AX minus Y, because there is no solution for that. But we can minimize AX minus Y, and the solution was that. So the solution was X is equal to the pseudo inverse of A multiplied Y. So here is again the pseudo inverse of BF multiplied this matrix. So what is the pseudo inverse of BF?
BF transpose BF.
Yeah, at least if you mention part of that, then I see you are following. Exactly, it's BF transpose BF inverse BF transpose then multiply what you have here. Okay, so multiply AF minus A plus BK. Okay, so I will go back to the slide and you have this equation, but it's I mean, maybe when you see it for the first time, you think that, okay, it's very complicated, but it's actually very simple because it's all of these equations that we will see from now on in today's lecture. There we are trying to minimize the cost function like that, and then we look at the unknown, and whatever the term with the unknown is, we take it to one side of the equation, we take the rest to the other side, and we will get something like that. And then KF, the solution for KF, usually we call it the KF star, would be the pseudo inverse of this matrix multiplied the known matrix in the right side. Okay, it's the same procedure. I will not repeat that for the next cases, but it would be, all of them would be the same. And sometimes actually instead of this, we write it is equal to BF plus multiply AF minus A plus BK, because as I said, BF plus means the pseudo inverse of BF. Any question here? Okay, that's the, so what we are talking about, we are talking about the case that a fault has happened in the dynamics of the system. So we want to see if we can match the model, which means that we have designed a controller for the nominal system. We want to see if we can design a controller for the faulty system to achieve, to have the exact model matching. So exact, as I said, exact is usually not achievable, but at least we can try to do our best, and our best would be to select KF star equal to pseudo inverse of BF multiply this matrix. And because controller U is equal to minus KF multiply X, and X is equal to AX plus BU. If you substitute U to X, you will get something like that. But it's not, I mean, you got the concept. It's just the substitution. Okay. What you need to pay attention is that what is the reason we are trying to match the model? And I just explained that because we have spent too much time to design a nominal controller, we are sure that the dynamics of the nominal controller are well designed. So the idea is when a fault happens, try to achieve the same result as we had, or similar, at least similar results. If the same is not achievable, similar results to the fault-free case. We don't want to spend time to redesign the controller for the faulty case. That would be another approach, by the way. Another approach could be, okay, to design a controller for all faulty cases that can happen, or you can imagine, design different controllers. It means that, okay, you should assume that, okay, the fault can happen here, so let's design a controller for this case. And then you need to go through that iterative process to refine or to fine-tune the parameters. But here, in order to avoid those fine-tuning and then iterative process, we design a controller for the nominal case, and we try to achieve the same or more or less the same response for the faulty case. So that's the idea behind model matching. There is an example here. In this example, I have assumed a fault in the dynamics of the system. So everything is the same. So B and BF are the same. If you notice here, only this element of the matrix A, which is actually, it is the dynamics of a two-cart system. I showed the system last week. It's two-cart connected to each other by a spring, and also there is a friction between the card and the ground. So this B1, it shows the friction coefficient. So in the faulty case, actually the friction coefficient suddenly has changed or has been doubled. So suddenly you have double friction. So which we have considered that as a fault. So first, if you focus on the nominal system, this A and B, you have designed a controller in this form. So U is K multiply X and K is equal to this. Now a fault like this has happened. And the question is, what should we select or how should we select KF, the state feedback for the faulty case? So what we do, we just go to the previous equation, we substitute everything here. First of all, we calculate the pseudo inverse of BF. So it's easy to calculate that. And then we have AF, we have A, we have B, we have K, we have everything. We have A, we have AF, we have B, we have K. So if you substitute in that equation, what you get, yeah, KF is, so if you substitute, what you get would be this. Okay, so it means that when the fault happens, you need actually to switch to this one. So we didn't, if you notice here, we didn't go and tune a new controller. We just used the tuned controller for the nominal system and found the controller for the faulty case. Is there any question here? Okay. And I believe that the idea should be clear why we are doing this. Okay. So as I said, in the model matching, we considered 3 different cases. The first case was having a fault in the dynamic of the system. I just showed you how to handle that. First of all, I said that when you have a fault in the dynamic, it should be state feedback, and then you saw the equation. The next case is if we have a fault in the sensor. So if you have a fault in the sensor, then C is not equal to C. Then C is actually CF. So instead of C, you have CF. But AF and BF, they are equal to their nominal value. So AF is equal to A, BF is equal to B. In this situation, if you look at this equation, it also shows that when you have a fault in the sensor, the controller should be in the form of output feedback. Okay, so you have an output feedback. As I said, for the exact model matching, you should have these 2 matrices to be exactly the same. So if we want to, we try actually to do this exact model matching here to see how we can, to see how much we can achieve that. So if you equate the left matrix with the right matrix, now you can cancel A from the both sides because A is being repeated. So then we have B multiplied K multiplied C is equal to B multiplied KF multiplied CF. Okay. So you know that, hopefully you know that if you have we have a lot of mathematics here, so I need actually to switch to the, just to remind you of what we had in mathematics. You know that if you have, for example, A multiply B is equal to A multiply C, it doesn't necessarily mean that B is equal to C. You know that. Do you know why? At least, do you agree?
Yeah.
Okay.
I think it's
To give you a simple example, for example, 1, 2, this is A, and B is 2 minus 1. This is B. If you multiply, it would be 0. I will take the same A, 1, 2, but this time B could be 4 minus 2. It is still 0. So this is C. So A multiply B is equal to A multiply C, but B is not equal to C. We know that, okay? But there is a but here. If we know that B is equal to C, then AB is equal to AC. I mean, the opposite is always true. So if B is equal to C, then we know that AB is equal to AC. About this problem that we are going to solve here. So we want actually to assume that KC is equal to KF multiplied CF. We know that having this matrix in the left side equal to the matrix in the right side doesn't mean KC should be equal to KFCF, but we know that if KC is equal to KFCF, then this equation will also hold. So that's the idea here. So the idea here is actually to gain. We are saying that KC should be equal to KFCF. So what does it mean? Again, everything is known here except KF. So this one is known, this one is known, this one is known, but this one is unknown. So KF is the only unknown here. So KFCF is equal to KC. Therefore, if you want to find KF, you need actually to find it as a pseudo inverse of the CF. Okay, so what is KF?
So again, we should use the pseudo inverse, but from the right.
Exactly, from right. That's actually the point that you should notice. It is the pseudo inverse from right. So it would be KC multiply the pseudo inverse of CF, but the pseudo inverse of CF from right, it is CF transpose CF, CF transpose inverse. So I don't need to I don't need you, of course, I don't need you to memorize this equation, but I do expect when you see the result here in the slide, you get why or how it has been resulted. Okay, so U is KF minus KF multiplied YF, and KF is K multiplied P, and P is like this. Just wrote you on the piece of paper that if you look at here, KF is K, C, and then this matrix. And now here you have C and this matrix, but because KF is equal to K multiplied P, this is only the P part. Okay. So this one should be, if you substitute this one here, you will get exactly what I said. There is a necessary condition to be able to write this result like this. And that condition says that the right null space of C of F or of CF should be a subset of null space of C, which is, don't know how much you remember from null space because we had the null space before. But just remember there is a condition. Maybe I can skip this, at least the proof of this. You have it here in the lecture, but I will skip that. Just remember there is a condition. If you want to use model matching for the case of having fault in the sensor, and this is the result, or KF, I don't know if I have the KF. And I don't have the KF here, I just wrote the KF on the paper. And if you want to use this equation, there is a necessary condition that you should check before you apply this. And the necessary condition is here. That says that the null space of C of CF should be a subset of null space of C. What does it mean? I have it explained in the next slide, but I will skip that. Okay, any question here? It's getting tiring. Let me finish this part by talking about the actuator fault. So it's very similar to the case that you had. Because of that, I actually can go faster. So here, AF is equal to A. There is no fault in the A. There is no fault in C. The only mismatch you have is B. So you have BF. So again, you have output feedback, and you are looking for the exact model matching. If you want to do that, you should have this matrix is equal to this matrix. So again, if you cancel A, then you have BKC is equal to BFKFC. One more time, it doesn't mean that necessarily BK should be equal to BFKF, but if BK is equal to BFKF, then this equation will hold. So we go for that case. So there is a necessary condition you will see, but what we are going to write, we are going to write BK is equal to BFKF. Again, everything is known, the only unknown is KF. Therefore, KF would be the pseudo inverse of BF multiplied BK. So BF, so KF is N multiplied K, but N is the pseudo inverse of BF multiplied B. Therefore, KF is the pseudo inverse of BF multiplied B multiplied K. It's very similar to what I said. If I want to summarize what we said about the model matching, we tried actually to have the exact model matching. And how to achieve that, we actually equated A minus BK equal to A minus or AF minus BFK in case we had a fault in the dynamic. And for the sensor and actuator fault, we used the output feedback, which means that A minus BKC was equal to A minus BFKFCF. It depends actually if you had a fault in the sensor or you had in the actuator. And then we simply using this pseudo inverse, we could match the model. It's not difficult. I mean, if you write it down on a paper, it's even easier to write it than looking at the equation, because when you look at the equation, you think that, okay, it's very complicated, but it's not. It's quite simple how you can achieve. One more thing that I need to mention before we go to break is that also for this case, there is a necessary condition. You can study that yourself, but just remember that there is a necessary condition. When you want to use the model match for the sensor or actuator, before using that, you should make sure if the conditions are fulfilled. Any question here before we go to the break?
Not really.
Okay.
Very straightforward.
I hope it means that it is clear, even though it's kind of tiring. You know that I'm not okay. Let me stop recording.